This is week 8 of thermodynamics course. This week we will see about Rankine cycle, the variations of Rankine cycle. The variations include how to improve your Rankine cycle efficiency. And we will also see problems on Brayton cycle. So this is a gas cycle, and that was a vapor cycle. And you will have in gas cycles you will have Otto cycle or diesel cycle and dual cycle. These are all cycles which come in gas power cycles. And then also we can see a problem on VCRS. So these are this week will include mostly on cycles, thermodynamic cycles. Mostly problems are on power cycles, and we also have problems on a VCRS, which is a refrigeration process. So on that we'll move on to see some problems on the cycles. So starting with, we have a Brayton cycle problem. So first is, we consider a simple Brayton cycle using air as a working fluid, as a pressure ratio of 12, and it says that the maximum cycle temperature is 600 degrees Celsius, and operates the compressor inlet at 100 kilopascal and 15 degrees Celsius. So which will have the greatest impact on the back work ratio, a compressor isentropic efficiency of 80% or a turbine isentropic efficiency of 80%. So we asked to use a constant specificated room temperature. So starting with, I'll give you a brief idea on what a Brayton cycle is. So in the TS diagram, I have plotted a Brayton cycle here. So you have two isentropic processes and two isobaric processes. So this will give a better idea. See, so we have two isentropic processes and two isobaric processes. So what will happen is, you have in compressor inlet which you are giving, and it will compress the fluid from 1 to 2. Ideally it should be an isentropic process, which is 2s, but that doesn't happen. So you go from 1 to 2, and then you supply heat to the fluid. You heat the fluid. You can have a combustion this thing to heat the fluid, or you can use a heat exchanger to heat the fluid. So you have two. The first is, you have a regenerator. So you are heating using the part of the fluid which is coming out, and then you have a combustion chamber, so where you combust and you increase the fluid's enthalpy. So it reaches state 4. From 4, then if you are expanding it to reach state 5. So this happens in a turbine. It's also, we assume it to be an isentropic process, and then there will be heat rejection. Here the cycle is an open cycle. Open cycle means, since you don't go back to the state where you started with, so you leave that to atmosphere. So 5 to 6 is your atmosphere, but this is your total heat rejection. It will be 5 to 1, but this being an open cycle, you leave at the turbine inlet exit or your regenerator exit. So this is the Brayton cycle. So going back to the problem, here they say that the pressure ratios is 12. So anything between your compressor and turbine, your pressures, your minimum pressure and the maximum pressure, because those two are isobars, so your pressure will be constant. So there the pressure ratio is 12, and they are saying the maximum cycle temperature. So after your combustion chamber or after heat addition, so that is your temperature which is given, maximum cycle temperature as 600 degrees Celsius. And they've also given that your compressor inlet is 100 kilopascal. So you know one of the pressure, and the other is your inlet is at 15 degrees Celsius. So now they are saying which will affect more, having a compressor isentrope of 80% or a turbine isentrope of 80%. So we'll see how to solve this problem. So first we have plotted that Brayton cycle here. We have two isentropic processes, 1 to 2s and 3 to 4s. So this should be ideal isentropic efficiency of 1, but we consider that your compressor and turbine is not fully isentrope process, so we have isentropic efficiency of 80%. So it goes from 1 to 2 and 3 to 4. And then heat addition and heat rejection shown by 2, 3 and 1, 4. So for the compression process, we'll first estimate what are the temperatures at each of the points. So 1 to 2s we'll find. So for an isentropic process, we can write as T2 by T1 equals P2 by P1 raised to power gamma minus 1 by gamma. So for air, your gamma value is 1.4. So from there we can find out T2s, your isentropic temperature after combustion. So when we know pressure ratio, which is given as 2L, and your inlet is 15 degrees Celsius, so 15 plus 2 73. So from there we can find out your temperature during isotopic compression will be 585.8 Kelvin. Now we know that your compressor efficiency is 80%. So you can write compressor efficiency as your minimum work. He'll be maybe in NS2 or you would have left. It's already 5. It's already 6. He would have left. Sorry. So your compressor efficiency is minimum work done by maximum work. So in compressor, your minimum work is happening in isentropic process, and maximum is your actual. So W min by W actual. So H2S minus H1 is your isentropic work divided by H2 minus H1, which is your actual work. So from this we can write enthalpies in temperature, and we can find out T2, so which will come out to be 660.2 Kelvin. Similarly, for expansion process, we can find out we know temperature at 3, the maximum temperature, which is 600 Kelvin. Using that, we can find out temperature at 4s. So T4s will be 429.2 Kelvin. And using the same approach, using turbine efficiency, we can find out temperature at state 4, which is 518.8 Kelvin. So now we know pressures and temperature at each of the points. So now we can estimate a compressor work and the turbine work. So compressor work when it's an isentropic process. So in that case, you will find out the work is 299.3 kilojoule per kg, and your compressor work, actual compressor work, so for 80% isotopic efficiency, is 374.1 kilojoule per kg. Similarly, turbine work is Cp delta T, and using the same T3 and T4s, we will get the turbine isotopic turbine work is 446 kilojoule per kg, and the actual turbine work is 356.8 kilojoule per kg. Now the back work ratio is nothing but how much amount of power you are generating out of how much amount of work you are consuming divided by how much amount of work you are generating, or to say how much amount of fraction of work which you are taking out of your power generated. So if you see in this case, what happens basically is your turbine is coupled with your compressor, and your turbine runs your compressor. So in that case, part of the work which is generated in the turbine will be utilized in running the compressor. So you are finding that fraction of work which is used in running the compressor. So that is the back work ratio. So for running a compressor of 80% isentropic efficiency and isentropic turbine, if you consider. So here the question was, which will be better, which will give you greatest impact on the efficiency of the cycle, having a less efficient compressor or a less efficient turbine. That is the question. So you consider just initially a less efficient compressor and efficient turbine, and then efficient compressor and a less efficient turbine. So these are the two cases which you consider, and we see what is the effect. So back work ratio for the first case with a less efficient compressor and efficient turbine will give you 0.8387, and similarly for a less efficient turbine and an efficient compressor, you see similarly you get the same ratio. So the two results are identical. So having any of that will have an impact on your efficiency, same impact on the efficiency. Moving on to the next problem, we consider a closed type ideal Brayton cycle as shown in figure, operating at a pressure or ratio of 12, with the air leaving the heat addition process at a temperature of 600. The air is at a pressure and a temperature of 100 kilopascal and 15 degrees Celsius. Then it enters the air compressor in the cycle. Note that both the turbine and the compressor operate isentropically. Treat air as an ideal gas throughout the cycle. Find the specific compressor work and calculate the specific heat addition. So this is a follow problem or a same problem considered previously. I think I should have put the previous problem next to this. It would have made a better sense. Okay, anyway, so here when you consider turbine, so your inlet is 1 and exit is 2, so you just apply an energy balance across the turbine. You will find out H1 equal plus W1 equals H2, or your work done is nothing but the change in enthalpy. So now you assume that specific heat capacity of the gas doesn't change with temperature, so it is constant or a perfect gas, and in that case and your enthalpy is independent of pressure, so you will write H as Cpt plus W in equals Cpt2. Then your Cp of air is 1.005 into your temperature is inlet is 15, so 15 plus 273 plus Wn equals 1.005 into your temperature at T2, which you need to find. So here the only unknown is T2. So T2 we can find out. We know the pressure ratio and we know the inlet temperature, and using isentropic process we can find out T2s, which will come out to be 585.8 Kelvin. So using the same energy balance equation, we substitute the temperature and we can find out the work generated, which is 299.3 kilojoule per kg. You see, that is what we got in the previous problem. And similarly we can find out the heat added. We are asked to find out what is the specific compressor work and the heat addition. So heat addition, we again put a energy balance across the combustion. So combustion inlet and combustion exit, it will be equal to the heat added difference. So H2 plus Q in equals H3. So again we are assuming H is a function of just temperature. So and Cp is constant. So we write Cpt plus Q in equals Cpt3. So we write Cp as 1.005, and we know T2 and we know the maximum temperature T3, so 600. We substitute that, so from there we can find out Qin is 288.6 kilojoule per kg. So that is the heat added. So if you see, if you try to calculate efficiency, you can calculate. So assuming a turbine is 100% efficient, So you have your work generated in turbine is 446, and out of which your compressor takes away 299.3. So 446 minus 299.3 is the total work which you will get out of the Brayton cycle. So that will be close to 146.7. That is 146.7, and your Q which you are supplying is 288.6. So 288.6. So that will give you 50% efficient cycle. So your efficiency of the cycle is to 50% for this case. Having a process, isentropic process in both compressor and turbine, but actually you don't get that, and your gas turbine efficiencies are gas power cycles are close to 30% or something close to that. So that's how you actual efficiency will be. And then moving on to the next problem, we have an industrial plant which is equipped with a regenerative gas turbine cycle as shown in figure. The air inlet condition to the compressor are 101.325 kilopascal and 27 degrees Celsius. The compressor pressurizes air to 10 times the inlet pressure. So your pressure ratio is 10, that's what given, and your inlet condition to the compressor is given, pressure and temperature is given. Then in addition to the maximum air temperature in the gas turbine is measured as 790 degrees Celsius. So you are telling maximum air temperature in the gas turbine, which will be your inlet, because in turbine there will be expansion pressure and your temperature will drop. So your maximum temperature will occur only at the inlet of the turbine. So that is your inlet to the turbine temperature is given as 790 degrees Celsius, or this is the maximum temperature which you will get after the heat addition. So that is 790 degrees Celsius. Also a temperature difference of 10 degrees Celsius is measured between the cold air stream leaving the regenerator and the hot air stream entering the regenerator. So a temperature difference between one side of the heat exchanger regenerator is given. The difference is 10 degrees Celsius. So I'll show you in the problem. So we'll see what else is given. The net mechanical power output is 106 kilowatt. So the net mechanical power is your turbine work minus compressor work. So that is the power which you get. Power output is given as 106 kilowatt, and the heat input source temperature is 2500 Kelvin. So this is the source from where you are getting heat, that is given. Also the compressor and turbine operate with isentropic efficiency of 87% and 85%. Now determine the heat rejection and addition rate for both the actual and ideal cycles. Determine the entropy generation rate in the combustion chamber. Determine the energy and the second law efficiency or exergy efficiency of the cycle. So if you see, this is the process which is the industrial plant is running. So as I told previously, your compressor inlet is where your air is taken in from the atmosphere, which is at 101.325 and 27 degrees Celsius. You compress the air from 1 to 2s, which is ideal case, but it's not an isentropic process, so it will go from 1 to 2. From 2 it goes to a regenerator where the fluid gets heated up by the fluid which is coming from the turbine. So that fluid rejects heat and leaves, and that heat is taken up by the fluid which is going to the combustion chamber. So this will get heated from 2 to 3, and your 3 is your inlet to the combustion chamber, where you are adding in heat from the source temperature of 2500 Kelvin, and it goes to state 4. So this is your inlet to the turbine, which is given as 790 degrees Celsius. So that is the hottest temperature you will get in the cycle, and here from there you will expand in the turbine, and it will go out at 5. Ideally it should be at 5s, but your entropy will be increasing because it's not an isentropic process. So it will go to state 5. From 5 you are using that fluid because this is at a higher temperature. If you dump it out, it's of no use. So you use that fluid which is at a higher temperature to heat the incoming fluid. So that's a better way of increasing efficiency. So if you do that, your your temperature comes down to state 6 and then you are leaving with exhaust. So this is how the cycle works. So we'll see how to solve this problem. So we'll first estimate what are the temperatures at each of the point. So T2s, we know the pressure ratio, which is 10, and we know the inlet temperature is 27 degrees Celsius. So from there we can find out using an isentropic process your temperature is 579.2 Kelvin. Now for an actual cycle, just like what we solved in the previous problem, your W isentropic by W actual will be your isentropic efficiency, and you are writing enthalpy in terms of temperature, assuming your Cp is constant and your it's independent of pressure. Using that, you can find out the temperature at state 2, which is the actual temperature at the compressor exit, which will come out to be 620.9 Kelvin. Now the next is we find out in your turbine exit 5s. So same isentropic process case. So you use we know the inlet to the turbine, which is 790 Kelvin, 790 plus 273. You substitute that and you know pressure ratio, so you can find out your temperature at the exit, isentropic temperature. So it will be 550.6 Kelvin. Now actual is, again use the isentropic efficiency of turbine, which is 0.85, and you can find out the temperature at 5. Isentropic efficiency of turbine is your W actual by W isentropic. So W isentropic will be a maximum work for in case of turbine. So W actual will be less. So W actual by W isentropic. This is the other way around for the compressor. So using that, we can find out state 5 temperature, which comes out to be 627.4 Kelvin. Now we do an energy balance for the regenerator. So if you apply an energy balance across this regenerator, you see the fluid which is coming in is at state 2 and at state 5, and one which is going out is at state 3 and state 6. So if you run an energy balance, so m dot 2 H2 plus m dot 5 H5 equals m dot 3 H3 plus m dot 6 H6. So that is enthalpies of streams coming in is equals to enthalpies of stream going out. So your mass flow rate will all be same, because there is no mass rejection or going out or coming in anywhere except at turbine in and exhaust. So throughout the cycle your mass flow rate is same, so mass flow rate gets cancelled out, and the enthalpy you can write in terms of Cp and temperature, assuming it's independent of pressure. So Cp gets cancelled out again because you are assuming Cp is constant. So you get T2 minus T3 equals T6 minus T5. Here in the problem they have given also a temperature difference of 10 degrees Celsius is measured between the cold air stream leaving the regenerator and the hot air stream entering the regenerator. So here cold stream is your state 2 to 3. Cold air sorry, also temperature difference of 10 degree measured between the cold air stream. The cold air stream is 2-3 because that is getting heated up, so that will be a cold stream, and 5 to 6 is your hot stream. So cold air stream leaving is state 3, and your hot air stream entering is 5. So T3 minus T5 is given as 10 Kelvin. So that's what is written here. So T3 equals T5 minus T10, T5 minus 10, or your T5 minus T3 is 10. So you replace it, rearrange it to find out state 3 temperature, which comes out to be 617.4 Kelvin. You know T5, which we have calculated in the using isotropic efficiency of turbine. So 627.4. From there we can find out state 3 temperature, T3. So now the only unknown is T6. So that we can find out using the energy balance of the regenerator, which will come out to be 631 Kelvin. So now we know all temperatures at each points and pressures. Now we'll calculate first we'll calculate the mass of air which is circulating, because we need to find out how much heat we are adding and heat rejected. So in the problem they have given your net work output is 106 Kelvin. So your work expression for the Brayton cycle is your compressor turbine work minus compressor work. So m dot A into H4 minus H5s minus m dot A into H2s minus H1, or and then you write it in terms of pressures, temperatures. So m dot A into Cp T4 minus T5, this is your turbine work output, and Cp T2 minus T1 is your compressor work output. So you subtract that into MA, which is equals to 106 kilowatt. So from there we can find out m dot A. We know Cp, we know all the temperatures. So substituting that, we will find out that mass of air which is required is 0.9241 kg per second. Then m dot ideal is this is for an actual cycle. Now for an ideal cycle, you need to take the isentropic compression expansion process, and you take the corresponding temperatures. So using that, we will find out that ideally required 0.455 kg per second, but in your actual cycle you need more mass flow rate because of this having a less efficient compressor and turbine. So you see close to double the mass flow rate which you are taking in an actual cycle. So next is we calculate how much heat is added and how much is it rejected. So actual heat addition is, so if we go back to the cycle here, you are adding between 4 and 3. So 2 to 3 is heat which you are heating up using the regenerator, using the exhaust fluid. So that will not be considered because you are utilizing the heat. The only heat which you are adding in is between 4 and 3 in the combustion chamber. So H4 minus H3 is equals to the combustion chamber heat addition. So for actual case, so it will be m dot A into Cp T4 minus T3. So this will be we have found out actual mass flow rate is 0.9241 into 1.005 is the Cp into your temperatures 1063 minus 617.4. So this will give me 413.8 kilowatt. You see, this is the heat which is added. And for ideal case, similarly you use ideal mass flow rate, which is 0.455 into your T4 will remain same, there is no change in T4, but your T3 T3 is also same because your heat exchanger you are assuming it to be 100% efficient, so there is no your inlet and exit to the heat exchangers are same. So your this the temperature will be same across the regenerator. So that will take into account both the temperatures, fixing the temperature in the combustion chamber. So only changes because of the mass flow rate. So because of that, your ideal heat addition is 203.8. So again, this is twice because your only change is in the mass flow rate. Now heat rejection rate can be evaluated as, so heat rejection is between 6 and 1. So in from 5 to 6 you are utilizing that to heat up the incoming fluid, so that is not rejection. So only rejection which is happening is between 6 and 1, which is going to the ambient. So m dot 6 H6 minus m dot into H6 minus H1, that is a rejection. So actual rejection is T6 minus T1. So this is again it will be 307.4. Your temperature is again same, you only changes mass flow rate, so that is 149.7 kilowatt. Now the next part of the question was to find out the entropy generation in the combustion chamber. So for that we will do an entropy balance across the compressor. So if you see, if you do an entropy balance across a compressor, uh, which is coming in is m dot a into s3 minus m dot a into s4, then your heat addition, which is q dot c cc, or combustion chamber heat addition, divided by the temperature. You are doing it at constant temperature, source temperature of 2500. So q dot cc by t of source plus sgen, this will be equal to 0. So if you see, we have written in terms of sgen, this is assuming it's a reversible process, so there is no other irreversibilities. So s dot gen can be written as your outgoing m dot 4 s4 minus m dot 3 s3 minus heat addition in, so q dot cc by t source. So this is what you get. Now you know mass flow rates, you know q dot, you know ts, we need to find out entropy. So this we can, corresponding to pressures and temperature, we can use an air standard table to find out entropy corresponding to this pressure and temperature. So pressure of 1013.25 and 790 degrees Celsius, your entropy is 6.376, and similarly for pressure of 101.325, sorry, your pressure ratio is 10, so your inlet temperature, third 3 is your, okay, 3 is also at same temperature pressures, which is 101.325 into 10. So this is again 1013.25 kilopascal and temperature of 617.4 degrees Celsius. So for that corresponding entropy 6.175. Now substituting it in the problem, your actual is 0.9241 into difference in entropy minus 413.8 kilowatt, which we calculated previously, which is added in actual cycle, divided by 2500. This gives me 0.02 kilowatt per Kelvin. This is the amount of entropy which is getting generated in the combustion chamber. Now the next is to find out the energy efficiency of the cycle and exergy efficiency, or a second law efficiency, or efficiency compared to the Carnot cycle. So in that case, your efficiency is nothing but work done by heat added. So work done is 106 kilowatt, which is given in the problem, and we have found out that heat which is added is 413.8 kilowatt. So substituting that, you see your efficiency is 25.6%. And similarly for exergy efficiency, you compare with respect to Carnot cycle. So Carnot, you say your work done, actual work done in the cycle, divided by Carnot work done in the Carnot cycle. So Carnot cycle, if you see, efficiency is defined as 1 minus T naught T2 by T1 equals to W by Q. So you take Q, so that will give you work. So Q into 1 minus T by T naught, T source, or T2 by T1. Here it's between the ambient and the source temperature. So ambient is 300, source is 2500, and Q which you have added is 413.8 kilowatt. So if you add that, it gives 29.1%. So this says that this is compared to Carnot, it is just 29.1% efficient. Or you can say, if Carnot is 100%, your cycle is 29.1%. This cycle is given as 29.1%. So that's what this says. Or to simplify it, if Carnot gives 100 kilowatts for the for some amount of Q, this cycle will generate 29.1 kilowatt for the same amount of heat supply. So that's the comparison, this thing for an exergy efficiency. So moving on, next question is, we consider an Otto cycle. So consider an Otto cycle as shown in figure that has a compression ratio of 6, a compressor efficiency of 85%, and an expansion efficiency of 90%. At the beginning of the compression process, air is at 101.3 kilopascal and 25 degrees Celsius, and the maximum temperature and pressure that occur during the cycle are maximum temperature is 1300 Kelvin and maximum pressure is 4 megapascal. Accounting for the variations of specific heat of air with temperature, assume Ts source temperature is 2000 Kelvin and T naught is 293 Kelvin. Find the net work and the heat transfer to the air during heat addition process and find the energy and exchange efficiency. So again, if you see, this is the Otto cycle, which is shown in a TS diagram. So 1 to 2 is again is an isentropic process. 2 to 3 is your isochoric process. So previously we had in a Brayton cycle, if you see, you had 2 isentropic process and 2 isobaric process. In an Otto cycle, you will have 2 isentropic process and 2 isochoric process. Isochoric is your volume is constant. So this is what is generally used in a petrol engines. So petrol engine runs in Otto cycle. So you will have 2 isentropic and 2 isochoric processes, and your heat addition and heat rejection happens during an isochoric process. So 1 to 2 is compression, 2 to 3 is your heat addition, 3 to 4 is expansion, and 4 to 1 is your heat rejection. And if you see in an engine, so 3 to 4 is where you get the power stroke, where you get generate power to run the engine. And compression is also is taken by the part of the work generated. So this what will happen in engine is you have a piston which will go down and generate power. It will be stored in a flywheel and it will be used to compress later. So to give an idea of link between these two, how does it happen in actual. Okay, so the properties of an air at 298 Kelvin is the inlet. So at temperature 1 you know the temperature, and then R of gas is 0.287 and Cp is 1.005 and Cv is 0.718 and gamma of air is 1.4. So heat added to the air is as follows. So temperature 1 is known. So from a table for air you can find out at state 1, because here they have said you have to account for the variation of specific heat. If it would have not been given, you can assume straight away using Cp you can calculate, but here for you can use Cv into T for internal energy, but as we have to account for Cp, you have to use an table, just like a steam table. You have to use for standard tables for air to find out the corresponding internal energy and enthalpies. So here you can find out U1 as 214.3 kilojoule per Kelvin and the specific volume is 0.85 meter cube per kg. So assuming an isentropic process, your exit T2S you can find out which comes out to be 614.3 Kelvin, and they are saying the compression process is not efficient and your efficiency is 0.85. So similarly, just like what we did in the Brayton cycle, we can the same approach. So to find out temperature at state 2 exit of compressor, which comes out to be 69.8 Kelvin. So corresponding to this temperature, we can find out your internal energy is 489 kilojoule per kg and V2 is 0.147 meter cube per kg. So P2 is nothing but P2 by P1. This is an isentropic process. So here we know V1 by V2 is 6, so we used that instead of here. Previously in the Brayton cycle we used T2 by P1. Here a compression ratio is given, how much you are compressing. So is V2 V1 by V2 is given. So V1 by V2 is 6. So you are using that, and for in an isentropic process, T2 by T1 equals V1 by V2 raised to power gamma minus 1. So from there we can use find out temperature at state 2, and then you find out actual temperature T2 using corresponding volume, specific volume, and the temperature. You can find out internal energy, which is 489 kilojoule per kg, and V2 is nothing but 6 times V1, sorry, V1 by 6, so it will be 0.1417. And similarly you can find out pressure at state 2. So P2 by P1 equals raised to power gamma minus 1 by gamma is T2 2s by T1. So from this we know all except P2, so we can find out P2 as 1274 kilopascal. So again during isentropic process in expansion we can find out T4s. So again here the volume the ratio will be same. So V3 by V4 is 6, 1 by 6. So and the temperature at highest temperature is at state 3, which is given as 1300 Kelvin. So 1300 into 1 by 6 raised to power gamma minus 1. So this will be equal to 634.9. And your actual temperature you can find out using the expansion efficiency, which is 0.9, and then you will get temperature as 701.4 Kelvin. Now for using this you can use heat which you are adding in. So Qin is Cv T3 minus T2, or you can find out from the table, and you can solve it. So here Cv is given 0.718 into T3 is known 1300 minus 669.8. This will come out to be 452.5 kilojoule per kg. Then your net work which you are generating. So net work is Cv T3 minus T4 minus T2 minus T1. So 0.718 into your temperatures are given. So it will come out to be 164.3 kilojoule per kg. So your efficiency is nothing but your work generated divided by total heat added. So 164.3 divided by 452.5, it will come out to be 36.31%. And the exergy efficiency is nothing same, your total work divided by work generated in the Carnot. So 164.3 divided by your heat added into 1 minus ambient by source. This will be 42.55%. So next question, we have taken a dual cycle. So just like Otto cycle, you have in Otto cycle you add isentropic, two isentropic, two isochoric. So if we see in a dual cycle, you will have this is an isochoric process, then an isentropic. First you will have isentropic compression, then you have isochoric heat addition, and then you will have isobaric process, and then an isentropic expansion. So you have 5 processes. Heat addition is split into 2 processes of isochoric and isobaric. If you see in a diesel cycle, so if you see 1, 2, 3a and 4 is your Otto cycle. So 1, 2, 3a, 4. So first isentropic, then isochoric, then isentropic, and then isochoric. That is your Otto cycle. And then from 1 to 2, then if you do an isobaric, 2 to 3c, and then come back by isentropic process, that is your diesel cycle. This mixture of both Otto and diesel is your dual cycle. So that is your dual cycle. So we see how to solve this problem. A compression ignition engine from a small truck is to operate on an air standard dual cycle with a compression ratio of 18. Saying due to structural limitation, maximum allowable pressure in the cycle will be 9000 kilopascal. So that is your maximum pressure which you can compress it to. So light diesel fuel is used at a fuel air ratio of 0.054. Your combustion efficiency can be considered as 100%. So whatever heat you are generating from combustion, you are adding it into the cycle. So that's what combustion efficiency of 100%. The cylinder condition at the start of compression are 50 degrees Celsius and 98 kilopascal. So now calculate the thermal efficiency possible with this condition, maximum thermal efficiency and peak cycle temperature under condition part 1 when you are having maximum efficiency, and see your minimum efficiency, and then you have corresponding to peak cycle temperature for that. So your limitation here is your 9000 kilopascal. So that is limiting how what kind of cycle it will be. So first case you have to see a cycle where you will have maximum thermal efficiency, and second case where you will have a minimum thermal efficiency. So we'll see this first before going to the problem. So we'll see how these three cycles are put together. So for if you have three cycles, auto, diesel and dual, and all three has same compression ratio, so that is if 1 to 2 where your compression process, isentropic compression, this ratio of compression, so that is V1 by V2 is same for all the cycles, auto and diesel and dual, and you are assuming same amount of heat is rejected. So heat rejection is between 1 and 4, so same amount of heat is getting rejected. So in that case this is how the cycle will look when it is superimposed. So 1, 2, 3A, 4 is your auto, then 1, 2x, 3B, 4 is your dual, 1, 2, 3C, 4 is your diesel. So that is what is shown here. So if you see for this case, your auto will have highest efficiency, or if you see work done is nothing but in a PV diagram, the area under the cycle, area enclosed by the cycle is your work done. So auto generates more work, and you will have for a given compression ratio, auto cycle will have highest efficiency compared to your diesel dual, and then last you will have a diesel cycle, and the same is shown in a temperature entropy diagram here. So similarly, if you have say maximum pressure, your pressure maximum is fixed, and in temperature is fixed, in that case this is how the cycle will look. So 1, 2A, 3, 4 is your auto, 1, 2B, x, 4 is your dual, and 1, 2C, 3, 4 is your diesel. So in this case it will be the other way around. So previously you saw auto is the highest efficient, here you will have diesel as highest efficiency, then comes dual, and then your auto. So for this problem, what we are saying, we are limiting the maximum pressure as 9000 kilopascal, but there is no limitation on your temperature. So but your heat addition which you are giving, that is limited, you cannot add more heat. So what you have a given amount of fuel which is injected, and that's a specific calorific value. So your how much amount of heat which you are adding in is limited. So initially this is how the cycle looks. So your condition at 1 is known, your pressure is 90 kilopascal, your temperature is 50 degrees Celsius, so 323 Kelvin. From this we can find out temperature state 2 using an isentropic compression process. So your state 2 temperature comes out to be 615 degrees Celsius. Again similarly you can put P2 is when you substitute for a compression ratio of 18, you will get P2 as 4851 kilopascal. You see this pressure is less than the maximum pressure which you can have. So you can increase the pressure. You can run the process and increase the pressure at constant volume. So like an Otto cycle, and then or you can run a dual cycle such that it goes till 9000 kilopascal, and then you do a heat addition at a constant pressure, or you can do a volume you can use a diesel cycle where at 4851 you start heat add all the heats. So for having a maximum thermal efficiency you have to go to an Otto cycle. So 1, 2, 3A. So this is how heat addition should be done. But if your during heat addition, if your heat added is more than 2x, your pressure will start to increase. So in that case you have to go to a dual cycle. So you heat at constant pressure till you reach 9000 kilopascal, and then rest of the heat you add it using a constant pressure process in a dual cycle. So we assume this is in a dual cycle process. So we find out Tx, temperature at x, where your pressure is corresponding to 9000 kilopascal. We know T2. So now this is a constant volume process. So P is proportional to T. So Tx by T2 is equals to P3 by P2. P3 is known, 9000 kilopascal. P2 is 4851 kilopascal. And T2 is known, we have calculated 888 Kelvin. So from this you can find out Tx as 1647 Kelvin. So this is the temperature at state x. Now we know air fuel ratio, so which is 1 by your fuel air ratio which is given, which is 18.52. Then this is nothing but mass of air divided by mass of fuel. So your Q added, total heat added is, in this case your state 2 to x and x to 3. So it is nothing but mass of fuel plus air into Cv Tx minus T2, which is process constant isochoric process, and then Mf plus Ma into isobaric process. So Cp into T3 minus Tx. So substituting all the temperatures, we need to find out T3. So your combustion efficiency is 1. So whatever heat is generated in the combustion will be added here. So if you see how much heat is generated, is nothing but 42500 into mass of fuel. So you divide it by mass of fuel throughout. So you will get air fuel ratio plus 1 into same Cv into the temperature, and C air fuel ratio plus 1 into Cp into delta T. So we know all, we can find out state 3 temperature, which comes out to be 3050 Kelvin. So either you can find out the total heat added, this is m dot f into 4250, and you can find out the work generated in 4-3 and 5-2. You can calculate the total work in the isentropic process, and you can find the net work which is generated, which is the area under this curve. and then use that divide by heat added, it will give me efficiency. Or you can use the direct efficiency formula for a dual cycle, which is expressed in terms of pressure ratio and the cutoff ratio. Pressure ratio is nothing but Px by P2, this pressure, and T3 by T2 for cutoff ratio. And this how the formula is, and the K is your gamma. So substituting this in the expression, Rc is your pressure ratio. So substituting this, find the thermal efficiency is 60.3%. And the peak temperature is nothing but 3050 Kelvin or 2777 degrees Celsius. Now minimum thermal efficiency in this case you will get is in the diesel cycle, so which is 1, 2, 3C4. So similarly you can find in this case your heat addition is at constant pressure, so Q is nothing but m dot AF plus 1 into constant pressure Cp into T3 minus T2. So substituting this, you can find out T3 as 2853 Kelvin. And similarly, you can use efficiency formula directly for a diesel cycle, which is expressed in terms of cutoff ratio. This is 1 minus 1 by Rc raised to power gamma minus 1 into the cutoff ratio raised to power gamma minus 1 divided by gamma into the cutoff ratio minus 1. So if we substitute all the values, you will get your minimum efficiency, which you will get is 53.3%. So maximum is 60%, your minimum is 53.3% for limiting case of pressure of 9000 kilopascal. So if you didn't have that 9000 kilopascal limiting pressure, you will have Otto cycle which will be more efficient and which will be greater than 60%. So in this case, your diesel cycle efficiency is 53.3% and your peak temperature is 2853 minus 273, which is 2580 degrees Celsius. So next is Rankine cycle. So again, Rankine cycle is nothing but you have two isobaric process and two isentropic process. So there in a Brayton cycle also had the same process, but all of it were happening in a gaseous state. None of it went into a two-phase state. In Rankine cycle you have it's in two-phase state. So another change is in Rankine cycle you had compressor, here you will have pump. So 1 to 2 will have pump, and your pump, pump work will be less than your turbine compressor work, because your specific volume of the fluid will be less in case of pump, that is liquid, right, water. So your work done is nothing but minus VdP, integral of minus VdP. So specific volume less, your work done will be less. So if you going to the problem, you have a compression and expansion are adiabatic. So reversible adiabatic, so it's an isentropic process. The change of kinetic and potential energies are negligible. You can assume dissipation and steady state operation. So maximum pressure is 40 bar, so that is your high side pressure, and your temperature at point 1 is 35 degrees Celsius. Temperature at point 2 is 35.14 degrees Celsius. So you see there is no much temperature difference. Average specific volume of liquid water is specific volume is given as 0.0010043. Then mass flow of water is given as 7 kg per second. The saturation states of water is given corresponding to 40 bar, which is the maximum bar, and this 0.05622 bar, and corresponding temperatures, saturation temperature and enthalpies and entropies are given. Now we need to calculate the thermodynamic states at point 2 and 4, that is your pump outlet and your turbine exit. Calculate the work and heat transfer during each process and calculate the efficiency of the cycle. So from 1 to 2 it's an isentropic process, so H2 equals S1. From pump, for pump you can write DHS V minus V dt, where a specific volume of liquid will not change much during compression, so because liquids are incompressible, so you can take V out, so integral of dP is delta P, so V into your max P, change in pressure, specific volume into P max minus P min. You know specific volume, you know your pressures, which is 40 bar and 0.05622. So substituting that, you will get your pump work is 4.017 kilojoule per kg. This is the enthalpy change across the pump. From this you can find out pump is nothing but H2 minus H1, m dot H2 minus H1 equals m dot into specific work. So H2 minus H1 equals dH. So from this you can find out enthalpy at state 2, which is 150.577 kilojoule per kg. Now similarly at state 4, this is an again isentropic process. S3 equals S4, which is equal to 6.0685. So from this we can find out the vapor fraction at state 4. So we know enthalpy saturated entropies at saturated liquid and saturated vapor enthalpies corresponding to 0.05622 pressure. So X4 is nothing but S4 minus S dash. S dash is your liquid and S double dash is your vapor. So substituting this, you can find out your dryness fraction is 70% or 0.709. Your H4 equals using the dryness fraction, you can find out the enthalpy at state 4, which is H4 equals your liquid enthalpy plus your latent heat into your vapor fraction equals 1861.02 kilojoule per kg. So enthalpy at state 4 is also found. So now we can find out the work done and heat transfer across each processes. So 1 to 2 is your compression process, where your change in work done is mass into change in enthalpy. So 28.1 kilowatt, and there is no heat addition, so Q is 0. In process 2 to 3 is your heat addition, so there your work done is 0, and heat addition is mass into S3 minus H2, which is 1858.1 kilowatt. And so if you see the pump work is very negligible compared to the other works. And process 3-4 is your expansion process in the turbine, so M into S3 minus H4, it will come out to be 6575 kilowatt, which is the amount of work which is generated. And then heat rejection, again the work is 0, heat rejection is m dot into H4 minus H1, so 12001.2 kilowatt. So efficiency is the net work divided by heat input, so turbine work minus pump work divided by heat added, so this comes out to be 35.3%. So this we saw, this is the cycle. So now how can we improve this cycle? So, and one more problem is your exit of the turbine is at two-phase state. So you have some liquid which is there at the exit of the turbine, which is generally very difficult to have in a practical system. You don't want liquid, so it will be damage to turbine. So you don't want that. So you also need to avoid that. So you need to bring this closer to the saturated vapor curve. So increasing the X value at the exit of the turbine. So that you can do one by doing this 3-4 process outside the two-phase dome. So in that case, you have to heat it some more, or you have to increase the exit pressure. So that is another way, and you can also increase the condenser pressure. So if you increase the condenser pressure for the same heat motor heat, then you will be going out of the two-phase loop, and in some cases you may also end up going above the critical point. So that is what is discussed here. So case of increasing efficiency, and also to the point you don't the major thing you want to avoid is the heat dryness fraction which you are getting. So you need lesser liquid in the exit. So all taking into account. So what will happen if you are lowering the condenser pressure? So if you lower the condenser pressure, so you get this shaded region, that is the amount of work which you are generating more. So if you see in this process, when you lower from 2, you are coming down to 2 dash. So when you compress from 1 dash, you go to 2 dash. So 2 to 2 dash is the amount of extra additional heat which you need to supply. And what this do is at the exit of the turbine you will have more liquid. So that is one of the disadvantages. Even though you are getting more work done, your efficiency increases and slight increase in heat added, but your dryness fraction is less at the exit of the turbine. The other way of doing is to superheat. So what you do is after the heat addition, you add more heat such that you are going from 3 to 3 dash, and then you are expanding. So 3-4 was the initial, so now you are superheating from 3 to 3 dash and expanding to 4 dash. So here there is addition of heat, and so there is increase in heat, and there is also increase in work which you are getting. So this shaded area is what is the additional work which you will get, and then advantage here is your dryness fraction also increases at the exit. The other way is to increase the boiler pressure. So by doing so, your moisture content will be more at the exit. So the dryness fraction will be less at the exit of the turbine, and then for the same maximum temperature. So this is for same maximum temperature, and then this green portion is what your additional work done which will get, and this red one is your decrease in work. So it will always be a based on this both to say whether we get an increase in efficiency or not. So now we move on and see a problem. So consider a steam power plant operating on the ideal Rankine cycle. So steam enters the turbine at 3 megapascal and 350 degrees Celsius and is condensed in the condenser at a pressure of 10 kilopascal. So determine the thermal efficiency of this power plant. B. The thermal efficiency if steam is superheated to 600 degrees Celsius instead of 350 degrees Celsius. And C. Thermal efficiency if the boiler pressure is raised to 15 megapascal and the turbine inlet temperature is maintained at 600 degrees Celsius. So you have 3 cases. So first is operating between 3 megapascal and 10 kilopascal with a temperature of 350 degrees Celsius. Then you are increasing to 600 degrees Celsius. That is the superheating case. And then what you are doing is you are raising the boiler pressure from 3 megapascal to 15 megapascal. So what will happen in that case? So if you see, these are the 3 cycles. So first is you are limiting to 350 degrees Celsius and 10 kilopascal and 3 megapascal. So second case is your pressures are same, but you are increasing to 600 degrees Celsius. Using this is a superheating case. In second, from using the same temperature of 600 degrees Celsius, you are increasing the boiler pressure to 15 megapascal. So first, we'll start with the first case, and we'll find out all the states. So at state 1, your pressure is 10 kilopascal, and your saturated liquid, the enthalpy is 191.81 kilojoule per kg, and your specific volume is 0.00101 meter cube per kg. And at state 2, the pressure is 3 megapascal. So this is being an isentropic process, S1 equals S2. And then we can find out the pump work as specific volume into P2 minus P1. So this gives me your work done in pump as 3.02 kilojoule per kg. So H2 is nothing but H1 plus your pump work, which will come out to be 194.83 kilojoule per kg. So now state 3 is pressure is 3 megapascal and your temperature is 350 degrees Celsius. So corresponding from the steam table, you will find out enthalpy at state 3 is 3116.1 kilojoule per kg, and entropy at state 3 is 6.745. So this being an isentropic process, you can find out at state 4 S3 is equals to S4. Your pressure is 10 kilopascal. From this you can find out dryness fraction at state 4, which is S4 minus SF divided by your entropy change during between SF and SG. So this gives me a dryness fraction of 0.8128 at state 4. Using this, I can find out enthalpy at state 4, which comes out to be 2136.1 kilojoule per kg. So now I have found out all the enthalpies values at all 4 state points. Now I can find out the heat added, which is nothing but H3 minus H2, which comes out to be 2921.3 kilojoule per kg. Then Q out is 4 minus 1, which is 1944.3 kilojoule per kg. So your efficiency is 1 minus Q out by Q in. So if you see nothing but Q in minus Q out is your this is a closed cycle. So your first law says your net Q is equal to net work done. So that's what is done. Q in minus Q out by Q in, which comes out to be 1 minus Q out by Q in. So 1 minus heat out 1944.3 divided by 292.1.3. This comes out to be 33.4%. Efficiency is 33.4%. So now moving on to the second case, there your state 3 is instead of 350 degrees Celsius is at 600 degrees Celsius at 3 megapascal. So H3 corresponding to that is 3682.8 kilojoule per kg, and H4 is 2380.3 kilojoule per kg. So Qn is H3 minus H2. So 3682.8 minus 194.83, which comes out to 3488.0 kilojoule per kg. And your dryness fraction at the end of expansion is 0.915. So see, previously your dryness fraction is 0.81828. So increase the superheat, you have increased the dryness fraction to 0.915. So in this case, your heat rejection is 2188.5 kilojoule per kg. So again, if you calculate thermal efficiency, you are getting 37.3%. So previously you were 33.4, now you have come to 37.3. So that's why thermal efficiency increases from 33.4 to 37.3% as a result of superheating, and also the quality stream increases from 81.3 to 91.5%. So if you see, there is a 10% reduction in moisture content when you are heating it from 350 degrees Celsius to 600 degrees Celsius. Now the third case was to increase the boiler pressure from 3 megapascal to 15 megapascal. So in that case, you know H1, you have to calculate the rest of all other enthalpies using the same process previously used. So if you see in that case, your enthalpy at state 2 will become 206.95 kilojoule per kg, and H3 is 3583.1 kilojoule per kg, and H4 is 2115.3 kilojoule per kg. And correspondingly, if you see, your dryness fraction is 0.804. See, previously for 600 degrees Celsius and 3 megapascal, your dryness fraction is 91.5%, but it has come down to 80.4% when you are increasing the boiler pressure. Now your Q in is 33 3376.2 kilojoule per kg, and heat rejection is 1923.5 kilojoule per kg. So your efficiency, if you see calculate, will get 43% efficiency. So your efficiency is increasing because of increasing the boiler pressure, but what happened is your dryness fraction is reduced. So your quality of steam has reduced from 91.5% to 80.4%, but your efficiency has increased from 37.3% to 43%. So moving to the next problem. Consider a steam power plant operating on an ideal reheat Rankine cycle. Steam enters the high pressure turbine at 15 megapascal and 600 degrees Celsius and is condensed in the condenser at a pressure of 10 kilopascal. If the moisture content of the steam at the exit of the low pressure turbine is not to exceed 10.4%, determine the pressure at which the steam should be reheated and thermal efficiency of the cycle. Assume the steam is reheated to the inlet temperature of the high pressure turbine. So reheat cycle is nothing but you are expanding in two stages. So you expand from 3 to 4 and then you heat again from 4 to 5 and then expand again. So in this case what will happen is your dryness fraction will increase. So previously if you expand from 3, you will end up having more moisture at the end, but using a reheat you are pushing that to state 6, which will have more dryness fraction, or quality of the steam will be more using a reheating. So this is how a reheating looks. So with 3 to 4 you expand in a high pressure turbine, and from there you heat it again and send it back to a turbine and expand fully. So that's the only change here. So so this is similar to the previous problem where 3 is 600 degrees Celsius and 15 megapascal. So from 3 to 4 so you assume the process is steady, and your 5 is again will be at the same temperature of 600 degrees Celsius. So the reheat pressure is determined from the requirement that the entropies at state 5 and 6 be the same. So 5 and 6 entropies is same. It's an isentropic process. So state 6 is at 10 kilopascal, which is given. So steam enters a high pressure turbine 15 megapascal and 600 degrees Celsius and is condensed in the condenser at a pressure of 10 kilopascal. So condenser is at state 6 is at 10 kilopascal. So P6 is 10 kilopascal. X is 6 is 0.896, which is the limiting case. As mentioned, if the moisture content is 10.4%, so your dryness fraction is 1 minus 0.104, which comes out to be 0.896. So using that we can find out the state 6 entropy. So it come out to be 7.3688 kilojoule per kg Kelvin. So S6 will be equal to S5, and then H6 also we can find out using the dryness fraction. It will come out to be 2335.1 kilojoule per kg. So using the same entropy and temperature of 600 degrees Celsius, from the steam table you will find out your pressure is 4 megapascal and your enthalpy corresponding to this entropy and temperature is 3674.9 kilojoule per kg. So we have found out for in a reheat cycle, so for your dryness fraction to be 89.6%, you need your pressure at the low pressure turbine inlet at 4 megapascal. So now to find out the efficiency, we know at state 1 inlet, which is 10 kilopascal, which will be at liquid inlet. So you can find out enthalpy and you can use specific volumes. and state 2 is at 15 megapascal, and S2 is equal to x1, and you can similarly you can find out entire your pump work is nothing but minus v dp. So specific volume will be constant because it's an incompressible fluid, so we can take specific volume out. So integral dp is change in pressure, so v into delta p. So specific volume is you can find out for 10 kilopascal. So your pressure will be 0.00101 meter cube per kg. So this into a change in pressure, which is 15,000 minus 10. So your work done is 15.14 kilojoule per kg. So your enthalpy at state 2 is H1 plus your pump work, which is 206.95 kilojoule per kg. So again you can find out state 3, which is at 15 megapascal and 600 degrees Celsius, which is given in the problem. So your enthalpy is 3583.1 and corresponding entropy is given. Using this entropy, and because S34 is your isentropic process, so S3 is equal to S4, and you know your calculated pressure, which is 4 megapascal. So for that same entropy and pressure, you can find out your enthalpy from the stream table. Will come out to be 3155 kilojoule per kg, and the corresponding temperature at that point is 375.5 degrees Celsius. So now we have found out all the enthalpies at each of the point. So reheat addition in this process will be H2 minus H3 minus H2 plus H5 minus H4 into mass. So you are using specific heat input. So H3 minus H2 plus H5 minus H4. H5 minus H4 is the reheat. So substituting all the enthalpy values, we'll get the total heat added is 3896.1 kilojoule per kg, and the heat rejection is nothing but H6 minus H1. So H6 minus H1. So substituting the value, we'll find out heat rejection is 214.43.3. So if you substitute in your your efficiency formula, so W by Q, it will come out to be 45%. So previously we saw increasing in 15 megapascal and expanding, your efficiency was 43%. So now again reheating to the process, we are able to improve the exit dryness fraction. Previously it was 80% and 43% efficiency. So using a reheat, we are able to increase the efficiency as well as improve the dryness fraction to 89.6%. So that was the limiting case for us. So we asked that our exit moisture content should be 10.4%. So for that case, we are reheating and we are able to improve the efficiency also by 2%. The next question is, consider a steam power plant operating on an ideal regenerative Rankine cycle with one open feed water heater. Steam enters the turbine at 15 megapascal and 600 degrees Celsius and is condensed in the condenser at a pressure of 10 kilopascal. So similar same data, and some steam leaves the turbine at a pressure of 1.2 megapascal and enters the open feed water heater. So determine the fraction of steam extracted from the turbine and thermal efficiency of the cycle. So you see, this is how the cycle will look. So the you'll pump the fluid and you heat it in the boiler, and then you send it to turbine. So from turbine you take away small amount of fluid at some intermediate pressure. You bleed off some fluid and you mix it with the fluid which is coming out from the condenser. So your turbine exit goes to the condenser, you reject heat, and then you pump it, and then which you are going in before you're going to the boiler, you mix it with the fluid which is coming out, bleeding off from, you take it from the turbine, you mix it up. So this will increase the enthalpy. So it's just like heat addition, and then you pump it again to the boiler. So you see 1 to 2 is the pumping, and then the pump inlet at 2 is mixed with state 6. So that will give you a fluid which is at saturated liquid state 3, and then we are assuming all ideal, so we are assuming that your open water feed water exit is a saturated liquid. So 2 is mixing with 6 and it coming out at 3, and then that is at 1.2 megapascal. So this is all happening at constant pressure, and then from 3 to 4 you pump again, and then you boil it in the boiler, and then expand from 5 to 7, out of which a small amount is taken at state 6. So if you take m dot is expanding at 5, so from 5 to 6 there is m dot, and then you are taking away small amount of fluid, so that will be at from 6 to 7 it will be m dot minus that small amount of fluid which you have taken out. So we'll see how to solve this. So we know at each point the process is same at state 1, 2, and you can find out at 6, at 5. So state 5 is you can find out 15 and 600 degrees Celsius, and P1 is 10 kilopascal, so you can find out there, and P2 1.2 megapascal is given, you can find out there. So pump work. So state 3 you are assuming it is saturated liquid, so you can straight away get it from the steam table. So similarly P4 is 15 megapascal, and you can find out at enthalpy at 4 using the pump work in the second pump. So you can find out enthalpy at state 4. So and state 6 also your pressure is known, so correspondingly take an isentropic process. So you know is entropy at state 5 for 15 megapascal and 600 degrees Celsius, which is given. So you can, for corresponding entropy and pressure, you can find out enthalpy and your temperature. So similarly you can use it for state 7. You know the pressure, which is 10 kilopascal, your entropy will remain same. So using that you can find out the dryness fractions and calculate your enthalpy. So using this you can find out all the enthalpies at each of the state points. So then now what you do is you will apply an energy balance. So energy which is coming in, which is equal to energy which is going out. So this if you apply an energy balance across this open feed water heater, so if you see so you assume y amount of fluid is coming out from the turbine at 1.2 megapascal. So y into H6 which is coming in, and 1 minus y is the fraction of fluid which is coming in from the pump. So 1 minus y into H2, this will be equal to 1 into H3. So apply an energy balance, you will get the same expression here, y into H6 plus 1 minus y into H2 and is equal to H3. So we know all the enthalpies. So from this we can find out the fraction y which you are taking away from the turbine. So this will be equal to 0.2270. So next is we will find out how much amount of heat is added and how much amount of heat is rejected. So that will be same. So Qin is H5 minus H4, and heat rejected is H7 minus H1. So H5 minus H4 into 1. So that will give me heat added is 2769.1 kilojoule per kg. And if you see in the condenser, you have already taken away y fraction of fluid in the turbine to take it into the open feed water heater. So in the condenser, so y part goes into the open feed water heater. So only 1 minus y part goes from at state 7 to the condenser. So 1 minus y into H7 minus H1. So 1 minus y into H7 minus H1. So this will give me 14886.9 kilojoule per kg, or an efficiency of 46.3%. So this is the last problem. So this is a vapor compression process, refrigeration. So R134A enters the compressor of a Any doubt in the previous problem?
No, sir. Okay, everything is good.
Okay. So this question, R134A enters the compressor of a vapor compression refrigerant system at 120 kilopascal as a saturated vapor and leaves at 900 kilopascal and 75 degrees Celsius. It is shown in the figure. The refrigeration, so this is how the vapor compression system works. So it's plotted in a TS. So you have isentropic compression, then you have isobaric heat rejection, and then you have isenthalpic process across the valve, and then 4 to 1 is again heat addition, or you can say that is the evaporator where you pick up heat from the space where you have to cool. 4 to 1. So this is how the cycle looks. So at state 1 they have given it is at 120 kilopascal and it is saturated vapor, and it is leaving at 900 kilopascal and 75 degrees Celsius. Then they are saying that refrigerant leaves the condenser as a saturated liquid. The rate of cooling provided by the system is 18,000 British thermal unit per hour, and then determine the mass flow rate of R134A and the COP of the cycle. Second case is determine the COP of the cycle if the expansion value is replaced by an isentropic turbine. Do you recommend such a replacement of a for refrigerant system? Determine the COP if evaporator pressure is 160 kilopascal and other values remain the same. And next is so previously you have pressure of 120 kilopascal. Now you have increased to 160 kilopascal. So that is third case. Then determine the COP if the condenser pressure is 800 kilopascal and other values remain same. So your pressure from 900 kilopascal you are bringing now to 800 kilopascal. So you have 4 cases. We'll see how to solve this. So from this is the ideal case 1, 2, 2s, 3, 4. But we don't have isentropic, so 1 to 2, 3, 4, that is your first cycle. So pressure at 1 is known, 120 kilopascal and saturated vapor. So from an R134A chart or a pH diagram or TS diagram you can find out enthalpy as 236.97 kilojoule per kg at state 1, and same for P2 which is at 900 kilopascal and 75 degrees Celsius. This is already given, so straight away we can find out that enthalpy is 310.51 kilojoule per kg. Then P3 they have given it is at saturated liquid. So 900 kilopascal you have to go find out saturated liquid. Enthalpy is 101.6 kilojoule per kg. And then 3 to 4 is an isenthalpic process across the valve. So H3 equal to H4. So using this now we can find out the work done. Work done is H2 minus H1. So it will be 73.54 kilojoule per kg. Then your heat load which you are getting from the evaporator is H1 minus H4, which is 135.4 kilojoule per kg. So now this from this we can find out the mass flow of refrigerant, because the cooling is given as 18,000 British thermal unit per hour. So 1800 is heat load into, so 1 kilowatt is equals to 3412.14 British thermal unit per hour. So by dividing by that will give me equivalent kilowatt, which is 5.275 kilowatts. So that is the amount of heat load in the evaporator. So divide by the specific heat load, which will give me 0.039 kg per second. So that is the mass of refrigerant in circulation. So COP is nothing but heat load by work done. So you can use specific heat this thing, because your mass flow rate gets cancelled out. So QL by W, this is 135.4 divided by 73.54 will come out to be 1.84. So COP is 1.84 for the first case. So next they are saying that instead of an valve you use an turbine, isentropic turbine. So if you use an isentropic turbine at state 3, your entropy is 0.3738 and your exit pressure is 120 kilopascal. So your compressor inlet is 120 kilopascal is given. So that will be your evaporator pressure as well. So So correspondingly 120 kilopascal and entropy of 0.3738, we can find out your entropy at state 4 is 92.98 kilojoule per kg. So we have to first find out dryness fraction, or you can follow in a chart, a TS chart, or we can find out in enthalpy straight away following in constant entropy line. So following that, we can find out enthalpy at state 4 is 92.98 kilojoule per kg. So then the turbine output is nothing but H3 minus H4. H4 is 101.61 minus 92.98, so 8.63 kilojoule per kg. This is the amount of work which is generated in the turbine. So your net work is nothing but the difference between the compressor and turbine work, 73.54 minus 8.63, which gives me 64.91 kilojoule per kg. Again, heat load is specific heat load is 144.0 kilojoule per kg. So COP is 2.21 in this case. So previously we had 1.84. Here your COP has increased because there is less irreversibility here because of the turbine, and your area under the cycle also increases. So your work becomes more efficient when you use a turbine. But practically we don't use a turbine because we don't want to handle two phase in a turbine, and it will become less reliable. The same case which we talked in the Rankine cycle. So similar problems will happen. So that's why we don't actually use a turbine in our home refrigerator or an air conditioner. So this COP goes from 1.84 to 2.21. So next is what happens when you reduce the evaporator pressure, increase the evaporator pressure from 120 kilopascal to 160 kilopascal. So in this case, correspondingly we need to find out state H1, which will come out to be 241.12, and your H4 is 101.61. So H4 will remain same because your H3 is 900 kilopascal. So H3 is equal to H4, but this state moves up, and your H1 is your saturated vapor at state 1 for 160 kilopascal. So that will be 241.212 kilojoule per kg. So substituting a COP, can directly find out the CP is 2.01. So increasing the evaporator pressure from 120 to 160 kilopascal increases your COP from 1.8 to 2.01. And similarly, decreasing your condenser pressure. When you decrease the condenser pressure from 900 to 800 kilopascal, your H3 value will change. So H4 value will change correspondingly, and your H2 value will change. So you again have to find out all the enthalpies from the chart, and substituting that you will find out COP becomes 1.89. So here too you see there is increase in efficiency because of reducing the condenser pressure. So that's it for today. If you have any doubts, you can ask.
No, no, sir. Everything is okay. Today, sorry, I joined late because Saturday they used to class at 7, and Tuesday used to class 6. There's a problem. Okay, no problem, sir. Everything
No
is
issues.
good.
No issues. Okay then. Thank you for attending. I will have
Thank you, sir. Thank you.
next class on Tuesday at 6.
Sure, sir. Sure, sir. And I will go through all the video. And I used to go through all the video, and everything is okay to me. Thank you, sir.
Okay. Thank you.
Thanks a lot, sir. Good night, sir. I'm leaving, sir. Huh?